Well, from the happy hubbub, I gather you're as eager as I am to get this over. So the last lecture is a review of what we've done before, actually, but it's focused on synthetic chemistry, in particular the synthesis of cortisone, which is a natural product. Cortisone looks like this. It's one of these steroids, which remember have 3 6-membered rings and then a 5-membered ring and various alcohols and ketones and so on. And in fact, this lecture originated with a book called Advanced Organic Chemistry, although I've used it so much that you can't tell it from the spine anymore, that was written in 1961 when I was taking organic chemistry by Louis Fieser at Harvard, who was the person I was having at that time for this course. He was a very good synthetic organic chemist, and he worked a lot on steroids. In fact, in 1936, he wrote this book, which is called Chemistry of Natural Products Related to Phenanthrene. Phenanthrene is a thing like 3 benzene rings, bing, bing, bing. So you see steroids are related to phenanthrene, so that's what this book was about. He was a stylish guy. Before I got there, it was reported that he walked around with a gold-headed cane. He had dropped that affectation by the time I arrived, but he still smoked like a chimney, although at that time he was on the Surgeon General's committee about smoking and health, and he absolutely quit then and went on, but he ultimately succumbed to lung cancer. So this is a way of homage to him. These are some of the steroids, the ones that are sex hormones. So very small amounts of them go around and make various things happen in your body. And they begin up at the top left with cholesterol. And you can see how various enzymes oxidize it, put a ketone here, an alcohol here, make an unsaturation, and so on to make all these important compounds. In fact, they were recognized as so important that work on steroids awarded 4 Nobel Prizes between 1927 and 1950. Right? And another 3 between 1965 and 1975, which were at least part due to work on steroids. Right? The awards in 1927 and 28 were determining the structure, and the one in 1965 recognized the synthesis of it. You have to know the structure before you can synthesize it, obviously. In fact, the ones in 19 and 27 and 28 were for determining the wrong structure. The thing they got the Nobel Prize for was this structure, which doesn't have 3 6-membered rings, bing, 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 like that. But it got settled in the 1930s. Okay? So by 1950, the Nobel Prize in Physiology or Medicine was awarded to Kendall, Reichstein, and Showalter for their discoveries relating to the hormones of the adrenal cortex, their structure and biological effects. So Kendall and Reichstein were organic chemists, and Showalter was a physiologist. Hensch's Nobel address said, the air of pessimism regarding rheumatic disease in general and rheumatoid arthritis in particular still finds expression in some of the modern writings and text. But then he goes on to describe how he had a patient at the Mayo Clinic a 65-year-old patient with an unusual story. A few days before he came, he was painfully affected with rheumatoid arthritis and had been for 4 years. Then jaundice suddenly developed, and within a week, most of his arthritic manifestations had disappeared. The jaundice lasted 5 weeks, and the rheumatic arthritis did not relapse until several weeks after the jaundice had disappeared. The thought occurred, instead of being relentlessly progressive, this disease, rheumatoid arthritis, may be potentially reversible, more so than we'd believed, perhaps rapidly so. So during the next 5 years, from 29 to 34, while the organic chemists were determining the true structure, observations were made on 16 patients with chronic arthritis or fibrositis in whom jaundice of different types and degrees developed. If the jaundice was deep enough and was characterized by bilirubinemia of the direct reacting type, the rheumatic symptoms quickly diminished or disappeared for varying lengths of time and then gradually returned. And furthermore, it was noted that during pregnancy, people lost that. So there was thought to be some hormone that would do this. They figured that out. You can read that yourself. Okay, so they took, Reichstein then, the Swiss chemist, took 1,000 kilograms of adrenal glands from cattle and was able to get 1 kilogram of dry residue from that and follow the activity as he parceled it out, including using Girard's ketone reagent T. Remember we talked about that's the thing that makes a hydrazone, and then it has a permanent cationic charge, so it'll take a ketone into water, then you can take it off and it'll go back into the organics. So that was a powerful way of separating these ketones. And so there we go. So they got 7 to 8 grams of a ketone out of that. So this was this fish hook to extract ketones, and we've talked about that before, so I'm just going to click through it very rapidly to show how it was synthesized, and now we know what it did. Okay, only when pure crystalline homogeneous substances were produced were they tested as far as possible biologically. So accurate determination of chemical structure was given priority. In nearly all cases, this could be elucidated in all its details. So now by the mid-1930s, they had what the structures were. And here were some of these steroids from the adrenal cortex, 29 of them, of which these 5 were particularly important as active, right? Now those 2, you notice, are on the top cortisol. It has an OH group in the top left here, and below it is cortisone, right, the ketone. Okay. So though that position 11 and the position 17 were particularly important then. You have to have that ketone at 11 to get cortisone. The introduction of an oxygen atom in position 11 of the steroid skeleton is one of the major difficulties in the synthetic production of cortisone. Why? Because it's so far away from any other functional group. It's not alpha to something or on the beta position where an alpha-beta unsaturation could be used, right? The preparation of this substance from desoxycholic acid still remains a long and laborious way, even when so many improvements to it have been discovered. If it is wished to obtain cortisone more simply, there remain 2 ways, either total synthesis or the discovery of a better qualified raw material that's close in structure to this that then you can convert into this for medical purposes. Both will be tried. The prospects of a total synthesis are difficult to assess. Okay, so it's going to be tough to do this. Either total synthesis or find a better raw material. And there's a footnote there. R.B. Woodward referred to the partial synthesis of an acid, which is already very closely related to cortisone, 9 April 1951 in Boston, Mass., and it gives a reference here. Okay, so this book that I talked about uses as an example of a total synthesis, Woodward's synthesis in 1951 of cortisone. And this is it, but we're going to go through it slowly. So this is the thing he wanted to make, right? It's got these 4 rings, A, B, C, and D. And obviously it's going to take a lot of steps to get there. And so the first goal is to make rings C and D. Why did I put a question mark on D? It's a 6-membered ring, not a 5-membered ring. So he's got something clever in the back of his mind when he thinks of that as the first thing he wants to make. And that will be a handle, that double bond on the far right, a handle to allow modification to make the ring a smaller size and put the functionality that you need on there. Okay, and this double bond at the top left of ring C is the thing that's going to allow us to get access to put the ketone on there. Okay, and down at the bottom, this ketone is a handle. It's at this position down here. This is going to be a handle to build the rings A and B. So we'll see how that works. So this compound was known and readily available and cheap, so you could get a lot of it to start with. Okay. So the first reaction he did was to build ring D onto that. How did he do that? What kind of reaction could build ring D, make these bonds that are highlighted in blue here? Anybody got an idea? Yeah? The Diels-Alder reaction, right? Okay, so he did that and do the standard old Diels-Alder reaction, and you put that ring on. But notice that's going to, when you put those, when the diene sits down on top of that double bond, the methyl and the hydrogen are going to be on the same side, right? Whereas over here, they want to be on opposite sides, right? So we better get that fixed up so that they won't have the wrong stereoisomer when we get to the end. Can you see any way to change it so that this hydrogen is no longer pointing down but pointing up? Yeah, Amy? Mitsunobu inverts an alcohol. If you have an alcohol, you can go from right-handed to left-handed, right? But there's no alcohol here. What functionality is handy? Raul? What's special about the position of that H?
It's on the same side.
Pardon me?
You want it to get the transfer.
We want to pull that hydrogen off and put it back on the other side. Is there any, there are a zillion hydrogens in here. Aisha?
Is it because it's next to a carbonyl group? So it's
Aha, enolate, right? Okay, so we want to go to that, and you do it with base. It's an enolate, and the trans isomer is more stable, so it goes all over there. Okay, via the enolate. And now we're going to make the ketones into alcohols. Can you think of a reagent that could do that? This is review. What kind of reagent is necessary? A reducing agent. Something that'll add hydride to the carbonyl. Any ideas? Pardon me? Hydrogen peroxide, good idea, everyone?
No.
Why? It's an oxidizing agent, not a reducing agent, okay? Okay, lithium aluminum hydride does the trick. Okay, so you do that. Now, what they want to do is get from this diol now over here to a ketone and an unsaturation. You already have an unsaturation here, okay? So let's think about how we do that. The oxidation levels turn out to be the same, right? So you just use acid to eliminate acid and water, so you can protonate and get that cation, right? But why get that cation? Why not protonate here and get the cation on the bottom, or protonate here and lose methanol and get the cation there? Well, the cation here is no good because it's a sigma. It's in the sigma system. It's not conjugated with the double bond. This one is allylic, but that one would be allylic too, right? But if you make that one, then the resonance structure is here. The vacant orbital, the low LUMO is here and here, right? And it's adjacent to the unshared pair on oxygen. So that's the one you want to do. So it takes off the one they want to take off at the top. You get that, right? Okay. Now you do an allylic rearrangement of OH, right? So, or you complete the allylic rearrangement. You took it off here and you put it on here. Now, what functional group do you have now? When you have OH and OR on the same carbon. Roy? Hemiketal. What does it do what does a hemiketal do? Loses alcohol, right? So the hemiacetal here, treat it with acid, protonate, lose that, and you've got the ketone now, right? So we've got it to here. But we need to get this OH off to get down to what he wants to build this over here. So he treats it with acetic anhydride, right? What does an alcohol do with acetic anhydride? The O attacks the carbonyl, acetate leaves. It's a substitution reaction at an acyl carbon, right? So you put acetate on here, okay? And now to get from here to here, we have to change an O on the ring into an H on the ring. What kind of reagent do we need? We need a reducing agent, right? So like a metal. So we use the zinc, right? So zinc comes in, gives electrons, the acetate leaves, right? So we generate this anion and that double bond, an enolate, but of course this is a resonance structure of it, and you put a proton on the anion down there. So he's got to that. So now ready for the next step. And the next step is to build ring B, right? And also to protect the double bond here so it won't react when other double bonds react, okay? And this thing here on B, building this thing on B, will be a handle to construct ring A, okay? And that double bond here gives you access to that place, which is, remember, where we need to put a ketone, which is sort of off in left field. Okay, so the first thing is to build ring B. Did you ever see a thing like that? Where from a ketone here, we build a whole 6-membered ring down here? We saw it 2 lectures ago, yeah. The Robinson annihilation, okay? So what we need is ethyl vinyl ketone, not methyl vinyl ketone, but ethyl, in order to get this extra methyl group in here. So this thing, which normally would be methyl vinyl ketone, is now ethyl vinyl ketone, so we'll have that methyl group on there. Okay, so ethyl vinyl ketone, right, generate the enolate, does a conjugate addition, or sometimes called a Michael addition, right? Make that enolate anion, protonate it, and now make the other enolate anion and have it attack the carbonyl to make the beginning of that double bond. What would you call that kind of reaction? If you make this enolate, react with this and end up with an alpha-beta unsaturated ketone. So you have a ketone attack another ketone to give an alpha-beta unsaturated ketone. Remember what you call that? Aldol. You still have a week, don't panic. Okay? Okay, so we're going to do an aldol reaction and then get over here. Okay? Now, what we do there in order to make this protecting group is treat with osmium tetroxide. We know that that makes a diol. We talked about that when we were talking about paracyclic reactions. Okay, so you can get the diol. Then you make the diol into this carbon with 2 more methyls on it. What kind of functional group is this? 2 ORs on the same carbon. That's a full acetal, right? And you make it by reacting a ketone, acetone, with the diol. Okay, so we're going to get this ketal or acetal. Okay, now we need to go across from here to here, right? And what we're doing is removing this double bond. Okay? So that's done with catalytic hydrogenation, right? And notice that's why we had to protect this double bond here, because it would have been destroyed. And if it was destroyed, then you'd have no functionality out here in order to change the 6-ring into 5-membered ring and put the other stuff on. So you had to first protect this, then get rid of this one. Okay? So now he's got this compound. And now he's going to work on ring D. Or pardon me, we're going to knock ring D off while we work on ring A so the whole slide won't fill up. Okay, so we'll just take that big thing up there and work on ring A. Now, what kind of reaction might make ring A an alpha-beta unsaturated ketone here? Any reactions that give alpha-beta unsaturated ketones? Aldol reaction. So that's what we're going to be looking for, but there's some problems, as you'll see. So we're going to do that. We're going to get this, and then an aldol reaction on that will make this. And we can get this by adding the anion here, conjugate to an alpha-beta unsaturated ketone here. What do we call it? What do you call that kind of reaction? The whole thing to start from here and build this ring. Build a ring. You said it before. Robinson annihilation we're going to do again. Okay. So that would be ready for the aldol. And now this double bond here is even closer to where we need it in order to make that ketone. Okay, now how do you do that? Now there's a problem. You have to make the enolate to do the Robinson annihilation. But this is where you form the enolate down there. You could remove one of these hydrogens and make an enolate, or you could remove one of those hydrogens and make an anion there, which would be allylic with an anion there, which is an enolate, right? So this one is called a vinylogous enolate. It's got an extra double bond in between, but still it would behave as an enolate. But the problem is that this one is more reactive. You want to make the enolate here, which you can do by removing one of those purple H's, right? And then having the anion be there as a resonance structure. That's fine, except that these are the ones that get pulled off easier. So what do? You go ahead, pull these off, tie them up somehow with something else, then get the other one, and then come back and take off what you had put on there. Use a protecting group. Okay, and notice incidentally that there's another H here that could also be pulled off that would have a resonance structure with the anion here. So there are lots of possibilities. Okay, you want to get that anion, which is like that anion. Okay, so first you have to protect the more reactive alpha position, and they do that by that's just abbreviating what's above. Make the enolate, attack that carbonyl, which has a leaving group on it. So the OCH3 will leave and generate this diketone, right? That's like a Claisen reaction that we talked about last time, where an enolate attacks an ester and the alcohol leaves, right? And then that gets attacked by an amine to give this, and that dehydrates. It's like making an alpha beta unsaturated ketone, except it has this nitrogen on it now, which helps out. The unshared pair on the nitrogen is stabilized by this. You can draw resonance structures that put charge on the oxygen. Okay, so this is like an aldol, an alpha beta unsaturated ketone. Also notice it's an enamine. Okay, so that's tied up the downstairs part, and now you can proceed with making the anion you want, right, which is going to add to there, and hopefully by a Robinson methyl vinyl ketone, or pardon me, it would be, methyl vinyl ketone this time, because the first time we had to put the CH3 in there when we used that enolate, pardon me, when we used this enolate over here. Now we don't need a CH3 here, so we don't need it. We can use methyl, except it doesn't work. The reaction doesn't work. So you have to do something a little more roundabout. Okay, so that doesn't work. But you can add it to, if you can't add it to methyl vinyl ketone, you can add it to the double bond here, do a conjugate addition to this sort of like a ketone, to that nitrile. Okay, so the enolate adds to this carbon, generate the anion next to the nitrile, then protonate it, and you've got that. Conjugate addition again. Okay? But the problem is there's the CH3 here could be either up or down, right? You could have added to either face of that anion, right? So here's what they said in the paper about that. The protected ketone was condensed with acrylonitrile, that's that compound with cyanide up at the top, in the presence of aqueous triton B N-T-butanol benzene. Triton B N, I'm not sure what the N is, anyhow, in T-but, oh, N, the I's left out, in T-butanol benzene solvent, and the product on basic hydrolysis yielded this long name thing as a mixture of two isomers. That's the problem, that's a mixture of two isomers. And that's just lore, whether you're going to get something like that, and sometimes you just have to suck it up. That's not, because there's no hydrogen you can pull off here, right, to make it come on the other side. That's just the way it is. So you got to throw away a certain amount of your stuff. Okay, so that's tough, right? So then they used strong base and water, which removed this protecting group, right? Made it back into the to the CH2 here, okay? And at the same time, it was strong enough that it hydrolyzed the nitrile to make a carboxylic acid there. So now, treat that with acid, protonate there, then protonate here, making that cation, but that can attack the carbonyl to get that, which can then lose a proton. So you've got a six-membered ring. So have we made it? Not quite, we got the wrong element there, oxygen instead of carbon at the bottom, right? So we need another carbon in the system, right? So protonate there, cation, eliminate, we got that double bond. Okay, but now we need to convert that into ring A. We need to put that extra blue methyl group on there, okay? So the way to do it is to use methyl Grignard. So the methyl minus adds to the carbonyl, and that is a leaving group. okay? And that's an enolate, so it becomes a ketone, and we've got this thing here. Okay, so we're getting closer now. Okay, you do an aldol and you have ring A. Okay? So this is a typical thing that happens. It looked like a Robinson annulation might go directly there, but it didn't work. So they do a workaround. Okay? So now A is all set. And now we need to work on ring D, which is, remember, a 6-membered ring, and it needs to be a 5-membered ring. Okay, so we'll put it up in the corner and start working on that. Okay, so the first thing what they're going to go for is to make it a 5-membered ring that has an ester group coming off, so you have that carbonyl group that we're going to want. Okay, so the first thing they do is treat it with acid and water. What do they do that for?
So the water.
What's that going to do with that compound? Aisha?
It's going to remove the acetyl and give it.
Right, now you get rid of the protecting group. You want to be able to work on that double bond now, so you take the protecting group off that you had on there when you were doing a catalytic hydrogenation. Okay, so, and now, we've got the diol, and now treat it with periodic acid. Do you remember what that does?
Oxidizes.
It oxidizes a diol to cleave the carbon-carbon bond in between, right, and make 2 carbonyl groups. Okay, so at first it adds, and then that's just an intermediate, transient intermediate, comes apart to give 2 aldehydes. And now how are you going to get a 5-membered ring?
Decarboxylation.
Right? You can make an enolate here, attack that carbonyl, or make an enolate here, attack this carbonyl. Those are going to give different products, right? What you need to do is to have this enolate attack this carbonyl if you want to make that compound, rather than have this thing form react with that one. Have this enolate react with that one and get the carboxylic acid down here. Okay, it turns out that base with aldol could be either that way or that way, and luck made it go the right way this time. Robinson annulation didn't work before, but this one worked the right way. Okay, and then we've got an aldehyde. We need the carboxylic acid. So you use dichromate oxidation, which we talked about, to oxidize an alcohol. And of course, you don't stop at the aldehyde, you go on to the acid. But you need the ester. So now they're going to make the ester. You could do Fischer esterification. But that's an equilibrium, and this stuff is becoming very precious because of all the work that you've put into it. So you want to do this in the highest possible yield. So they use diazomethane, remember, which is the way of doing it really, to change the acid into methanol, into a methyl ester in really high yield. Okay, so that's a dangerous compound to work with. It's much more expensive and cumbersome than doing a Fischer esterification, but it gives a really high yield, so that's what they did. Okay, so now they had the ketone here, and now they made it into an alcohol. Now this looks nuts, right? They already had the ketone there, which is what they want, right? And the double bond here, right? They've got it. Why did they backtrack? They backtracked because it was already known from 1918. Well, so they used borohydride this time to reduce the ketone to an alcohol. If they'd used lithium aluminum hydride, it would have reduced the ester to an alcohol. They didn't want to do that, right? So you have to choose the reagents carefully when there's possible competition like that. Now, it was 1909, it was found out that this alcohol can be separated, the 2 enantiomers, easily. That was already known like 50 years before, right? So they backtracked in order, see, all this stuff they've been doing started with achiral material. So they've got both right and left-handed stuff there, and they want only the one enantiomer ultimately, and someplace they're going to have to separate it, and this is where they do the separation. Because it turns out, if you put this in together with this digitonin stuff, which itself, notice, has a 6,6,6,5 steroid inside it, this complicated sapogenin as it's called, then those things come together and what precipitates is just one hand. The other one stays in solution, right? So this was obviously Lohr. But anyhow, they got that. And now, having made this, it turned out that previous studies of cortisone had shown that if you had this, you could make this from it, right? So this is called a total synthesis, but in fact, it's a formal total synthesis or a relay synthesis, because by the time they got here, they had very little material. So they couldn't do a bunch more steps, but it was known that those steps could be done because people had already done them, right? So they could then start with material which had been made from cortisone or some other sterol and then carry it through, but there was no point in doing it because people had already done those reactions. And this is the paper. This is the whole paper that described the total synthesis of cortisone. Woodward was not a man of many words, right? There actually had been a previous paper of about 2 pages about making the precursor that we showed, right? So he then had this. He reduced this double bond, right? But notice it didn't reduce this one and didn't reduce. It did reduce this one and this one, but didn't reduce this one. So again, this is testing the various methods you're using to make sure what's going to react and what isn't. Why didn't they want to get rid of that double bond? Because that's the one that's going to give them the handle to get that ketone in up there, which is a very difficult position, okay? So, and then they could do sodium borohydride that made the alcohol that we showed you before, right? But notice that the borohydride didn't attack here, it only attacked down here, okay? Then they made the acetate from that alcohol, and now they've got to convert this to cortisone. At this point in our synthetic work, our synthetic work intersects the lines previously laid down in the extensive prior investigations by many groups. So he goes through some of these groups. Hyman and Fieser, that's the guy that wrote this story, right, have recently converted the acetoxy ester 3 into this compound 5. So here's the reference to that. It was work in 1951. So what they did was to, let's see, okay, that's, whoa, there's a lot of stuff here, okay. Reaction 4, reference 4, reference 5, then reference 6 puts that thing on up there, and then reference 7 puts the alcohol in, or whatever. And finally, the double bond by Maddox and Kendall. Kendall, remembers the guy that got the Nobel Prize, the chemist at the Mayo Institute. Okay. So that did it. They had it. They'd solved the intellectual, artistic problem of how you can start with simple available compounds and make cortisone, right? But what was the yield, right? Think a bit about yield, okay? Suppose you do 39 steps, and each step has an 80% yield, which isn't so bad as you've found in lab, right? Okay. Then the overall yield is 0.01% if you take 0.8 to the 39th power. But there's a different way to go about it, what's called a convergent synthesis, where you make several big pieces and then link the pieces together. So the distance in number of steps from any one starting material to the product is smaller than having all 39 in a row, right? So you could start with something that does 9 steps, say, that makes A, another 9-step sequence makes B, another makes C, and another makes D. And now you put A and B together, and C and D together to make E and F, and then you put them together. And now the distance is only 9 steps plus 2 steps for any given starting material, and you get a 9% yield. Right, so convergent synthesis has real advantages. Now, how about a practical cortisone synthesis that could make something that people could afford to use? Well, there's cortisone. Remember, that's what the Nobel laureate said. There are 2 things you can do: either do a total synthesis or get a better starting material than was then available. So choose an appropriate, readily available starting material. Okay, desoxycholic acid, a bile acid, which you can get from slaughterhouses or get the glands from which to make it from slaughterhouses. Okay, it comes from ox bile. So in 1946-49, Merck made a kilogram of cortisone from 600 kilograms of that bile acid, which came from an enormous amount of stuff from the slaughterhouse. But notice why that was a good starting material. It has all the rings in place of the right size, right? Properly, and it's properly methylated. So it's got the skeleton, the carbon skeleton. It's got all those things in the right stereochemistry, right? It's got here functional groups at or near at least some of the proper positions, right? You're going to have to fiddle around out here somehow, right? But how are you going to do that, right? Well, you could imagine they were able to go in 12 steps to that, and we're not going to go through what those next 20 steps are that allow you to get the red thing. But you could imagine things like do a bromination at a tertiary position. Maybe you could do that. Then eliminate HBr. Maybe it could go the wrong way. Then maybe you could cleave the double bond and make the ketone. Then maybe you could do alpha bromination adjacent to the ketone, and then make alcohols from that. Something like that. You can imagine. That's not what was done. That wouldn't be 20 steps, right? It didn't work that way. But you can imagine ways that you could get at it. Okay, so they did it in 20 steps. Okay, so then they got cortisone. And they could sell it in 1949 for $200 a gram, having made it by a 32-step sequence. Okay? But there's another compound called diosgenin. And diosgenin also has the right set of rings and the right stereochemistry and functionality in a good place, right? And it's abundant in a Mexican yam. And Russell Marker, who was an organic chemist at Penn State University, went exploring. He sort of quit and went down to Mexico and looked around to see if he could find natural things that that contained a lot of this. And the roots of this yam, some of them are 20 or 50 kilograms, and a fair percentage of it is this stuff, right? So he was able to find a good source of this. Right? And it could be converted in 5 steps into progesterone, a female hormone. Right? And so in 1943, he got 10 tons of that yam, and from it made 3 kilograms of progesterone, which was then worth $250,000, which is in 1943, which is like, I don't know, $5 million now. He had the world's supply of progesterone. Right? Okay? Which is a pregnancy hormone. And so it was selling in 1955 for 48 cents a gram, right, instead of this $200 a gram stuff. Okay, but there's a problem if you want to get cortisone this way, because there's no foothold to get at that position rather than that one or 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 that one, right? How are you going to put the ketone in, right? And this is where it was found, actually, by this guy here, or by his research group. Frederick Heil, who was an undergraduate and graduate student here, was the director of research at Upjohn. And at Upjohn Research in Kalamazoo, they found out that they had some of this, a mold started growing on a dish that was in a windowsill. And when you put it on here, it put a ketone in that position. Okay? Pardon me, put the alcohol in that position, but then once you got the alcohol here, they are home free, right? Okay, now, so Woodward had done the total synthesis of cortisone, and he did a lot of total syntheses, like the strychnine synthesis here. I thank Professor Saunders, who took these pictures. He was still a graduate student at this time in 1954 when strychnine was synthesized. The interesting thing about Woodward, there was a real cult of personality, still is, among older people, because young people don't know who he was anymore. Because he was such an artist. I mean, designing these things is an art, but you have to really know a lot to see the art in it. And his Nobel citation actually said for his outstanding achievements in the art of organic synthesis. I don't think there's ever been another Nobel citation that said art in it. So he made a lot of these things. Here was strychnine, a very challenging thing. And so when they got it done, they drew it very carefully on the blackboard, and the postdocs who had worked on it. Alice was a faculty member from the University of Bristol in England. Hunger was a German. Daneke and Schwenker were from Switzerland. And Kava was an American who went to be a professor at Penn, right? But you notice when Woodward got the Nobel Prize, his colleagues wrote this in Science magazine: Woodward's style is polished, showing an insight and sense of proportion that afford him strong convictions and a well-developed dramatic sense. So you can see just the way he's lighting his cigarette there looks sort of dramatic to me. And look at his signature. He always signed minuscule signatures, right? There, R.B. Woodward, right? And they also put a check mark on it when they finished the synthesis. And down in the bottom wrote fecund. So you know Latin. But that, as I talked to Victor Bears in the classics department, that's not a proper Latin word. But fecerunt means they made it, right? So that's what, they almost got it right, evidently, writing that on the blackboard. But one of the hallmarks of Woodward's style was that he always wore the same color blue suit and blue tie. So that's a Woodward blue tie. And in fact, students painted, one Halloween painted his parking place that light blue. And I know where they got the paint, because I got it. Okay, so then in 1973, they did this real pinnacle of synthesis, the synthesized vitamin B12. You can't imagine all the problems that were faced by this, and it was a collaborative work between Woodward and Eschenmoser's laboratory at the ETH in Zurich in Switzerland, right? And in connection with this work is where Woodward discovered stereochemical control by orbital symmetry. Those are called the Woodward-Hoffman rules, con rotation, disrotation. And it was while working on this that he discovered that. Okay? They had 100 co-workers at these two labs working on this. All of them very, very talented, including this guy, Yoshito Kishi, who was a faculty member from Nagoya University, who had come to work on this project with Woodward. And this is what Woodward wrote about him when in Pure Applied Chemistry in 1971, he wrote about working on the B12 synthesis. The first preparation of corigenolide afforded striking testimony of the experimental skill of its discoverer, Dr. Yoshito Kishi. All the operations had to be conducted with every conceivable precaution in respect to purity of reagents, exclusion of oxygen and moisture, and with the greatest possible speed. So he was a real wizard in the laboratory. And he then joined the Harvard faculty after that, and then succeeded Woodward as professor of Harvard after Woodward's untimely death. And we've seen his name before, not for this. He ultimately synthesized paletoxin, this compound, which has C123H2O13NO53, right? It's got 42 functional groups, which were protected in 8 different ways. So you could remove some of them, put others on, and so on. Right? It has 62 stereogenic centers. It has 7 double bonds that could be either E or Z. So there are 10 to the 20th stereoisomers possible, right? And it was done convergently. So they made 8 different pieces, right? And then put those pieces together. So you'd get no yield at all if you did this in a sequential synthesis, right? But they actually made it, right? And it was not, although that was just a tour de force, it's related to practical stuff, because we talked last fall about this Azi drug, which has a lot of similarity to that, right? And the week after we spoke about it in class, the FDA approved it for treating metastatic breast cancer. Remember, we talked about whether that was pending at the time. And you'll notice that the leader of this group was Kishi, the guy, he had cut his teeth on paletoxin for synthesizing things like this. So that this drug can now be made synthetically, practically, and sold as a drug that way. It's just incredible. Okay, so organic synthesis has come a long way from urea. Remember what Wohler wrote to Berzelius in 1828 that about the experiment when he reacted cyanic acid with ammonia and tried a crystalline substance appears which is inert, behaving neither like cyanate nor like ammonia. So that's the story, but first a little bit of thanks and credits. First to George Maxfield, who was my high school chemistry teacher. I remember his doing it. We'd be working on something. He wouldn't be doing anything at all, and he'd go like this. And the other thing he did was he said, you make something, you put it in a bottle and sell it to your neighbor. So I'm quoting him. And there's Theodore Roosevelt Williams, who was my first college professor at the College of Worcester. And then Fieser we talked about, and Bartlett. And Conant was his boss, who had two PhD advisors, a physical chemist, T.W. Richards, who got the Nobel Prize, and organic chemist, E.P. Kohler, who was these three pictures were all taken at Yale. That was when Stirling was dedicated. This was at a meeting in 1931 when Bartlett was just 24 years old, right? And but Kohler never went to meetings. He never left Harvard. People would come there to talk to him, but he wasn't interested in that. He just taught all the time, right? And Kohler's the one that that finally resolved allene. Remember we talked about that Van Hoff had predicted it, but Kohler's the one that made it. So Kohler was a student of Remsen, who was at Johns Hopkins, and Richard studied with Ostwald. Remember the guy that didn't believe in atoms? And then the next generation back was Fittig, who discovered the Pinacol reaction, right? And the one person I couldn't find a picture of was Carl Schmidt, who was at Riga in Latvia. But he was described by Ostwald as a tall, thin man with a small head, a strong nose, ice gray hair, and a thin beard, and a very nice person, right? And Schmidt had worked both with Liebig and Wohler. He was first a student of Wohler who recommended him to Liebig. Fittig had worked with Wohler. So we're back to those guys, and then to Gay-Lussac and Berzelius, and then to Berthollet, who was a colleague of Lavoisier and wrote how to name compounds. But there are some other heroes to whom we should pay homage, even if they weren't our ancestors. You know who this is? Right. Who's this? Emil Fischer, the last lecture. Kerner, the other guy who did a real proof in the 19th century. James Clerk Maxwell, right? Remember him? Cooper, right? The tetravalence of carbon. Lavoisier. And Robert Hooke. There's no known picture of Hooke, right? Because Newton probably destroyed it. That's true, right? But this is a picture of somebody using Hooke's apparatus. And Hooke was a hunchback, and he drew that picture. And I like to think that might be a self-portrait, although I sort of doubt it. But Hooke was certainly a great guy. And then, of course, we have a lot of people we have to pay homage to at Yale, too, like Silliman with his T-shirt that says, "How do you know?" Or a giant. Who's this? Gibbs, right? And Onsager. Those two, Gibbs was arguably the smartest guy of the 19th century, or certainly among the top half dozen or so. And Onsager was the same in this century, right? And I actually had Onsager as a colleague. We overlapped for a few years, okay? I mean, like Feynman was in awe of Onsager, right? And when Onsager got the Nobel Prize, when they called to inform him, he asked what for, because he had done so many things that could have gotten the Nobel Prize, right? And then, you know who this is? Chupka. These are the colleagues I've enjoyed having around for a while, and he came in and told people how he determined the heat of vaporization of carbon. And that one, you know, Weiberg. And here's Professor Ziegler, right? these are people who gave lectures in the course, right? And of course, you know who's next. Not a faculty member, but a graduate student from Yale. Right? And then someone who's almost from Yale, Les Lazarovich, who spoke to you last semester. He's from Israel, but he comes so often to visit that we'll call him an honorary Yaley. Okay? And then these people we quoted. Remember, he's the guy that originated How Do You Know? Hourly, right? And she's the one that does it now. And here, this is my wife, and that's John's wife. And this was night before last, over across the street here, at a meeting of the Connecticut Science Teachers Association, when this plaque was awarded to my wife and she's sitting back here. And next to her is the biology professor from Bowdoin, whom I've quoted, and she's sitting back there too. And then these are the kids. I mean, it's the next generation, right? And they're here with Caroline Doty. Do you know who Caroline Doty is? A basketball player at UConn. So we've gone to UConn games. So I don't know what they're going to do. They might be scientists. They might be scientists. They might be basketball players. They might be lawyers, doctors, right? But you guys are going to be that too. And you're going to be their teachers, right? Or their healers. Or, Lord forbid, defend them in court or something like that. Right? Okay, so there you are. So I want to thank all the students, not only you guys, but many years. So thanks. We'll have a review on Monday in room 110. There's going to be a symposium here. So at class time on Monday, we'll have a review down the hall. And good luck on the final. And that's it. Thank you.